Hi, and welcome to this fourth clip in this A2 Thermodynamics series. And in this one, we're going to look at a second Born-Haber practice cycle. And in this one, we're going to look at the reaction between magnesium and chlorine to produce magnesium chloride. So we're going to ask the cycle to calculate the delta HF, the enthalpy of formation, which you'll be used to in year 1 of AS chemistry. And we're going to ask the Born-Haber cycle to do this using some of the definitions that we looked at in some of the earlier clips. And so we will start off with our elements in their standard states at 298. So that will be chlorine as a gas and magnesium as a solid there. And we know that we're going to be asking to create the delta HF, which is going to be the question. And we're going to assume in this example that it is an exothermic. We'll work that out when we get the final answer. And we are going to produce magnesium chloride as a solid at the end there. And so what we need to do now is go through each of the steps that we need for this cycle and get to the final calculation. So in the first instance, what we will do is we will take our magnesium solid, and if you remember, we have to make the metals into the gaseous atoms. We have to do that so that we can ionize them at a later date, and we can only do that by definition by ionization, which has to be in the gaseous state. So we'll do that first step there. That will be the atomization for the magnesium. We will then ionize the magnesium first. We'll do that once to create an Mg plus gaseous ion. That will kick out that electron, and we'll still have the two chlorine diatomic molecule there. Personally, I like to look at each half in turn and get it to its final position. So what I'd like to do is ionize magnesium for the second time to create the second electron, knowing that magnesium is a group 2 metal, and so it's going to be an Mg2 plus ion. So I'm going to have to take out that second electron, and I'd like to get to this position before I then start to deal with the chlorines. It just means I find it easier to not miss out a step. It's not going to get you to a different answer, because numerically it will all add up to be the same value at the end. It's just the order of the steps which are different. Just pay attention to an exam if you're given predefined steps, that's all. But personally, if I'm doing these from scratch, I like to do them individually, with the metal ion first, followed by the non-metal ion. And I then need to start with the chlorine, and in order to do the electron affinity, so the reverse of the ionization energy, if you will, I need to take my diatomic molecule and split it in half so that I have the two chlorine atoms, again in their gaseous state. Now, depending on the question, this may be given as an atomization, which is by definition the creation of 1 mole of a gaseous atom, or for non-metal diatomics, you may be given the bond dissociation energy. The bond dissociation energy being the energy required to break 1 mole of molecules, which will give you 2 moles of chlorine atoms. And so sometimes you just have to be careful of what you're given. But if I'm being given the atomization, I'm going to have to double that numerical value when I get to my calculation. So now I have my magnesium as an ion, I have my chlorine as an atom. I can now take those chlorine atoms and ionize them, or more correctly, give them their electron affinity and give them their electron. So each chlorine would pick up an electron. So we had 2 electrons from the magnesium that would be given 1 apiece to the chlorines to create the chloride. I now have everything in the gaseous state. I now have everything in its ionic state. And so the final step will be the lattice enthalpy. I'll take this one as a positive value this time. And so remember, lattice enthalpy can be in either direction. You would just look at the sign of the value that you're given. And this would be the first electron affinity. Remember from the previous example, what we said was the first electron affinity is an exothermic process because you're making a bond between the atom and the electron, or the electron and the nucleus of the atom. And the second electron affinity, if it were to have one, would be negative. It would be an endothermic process. And you see that with oxygen going to oxide O2 minus. So if you remember from the start of this one, we said that the question was trying to get us to calculate the delta HF of this reaction. And so delta HF is going to be the result of a numerical sum. So I'm wanting to go from essentially the initial state we started to this final ionic state, but I can't go directly. So in a similar style as Hess's law from previous modules, we've got to go in an indirect route via an alternative route, which means that I need to mathematically add up all of these values. And so you'd be given these in a question. You would generally be given all of the values bar 1, that 1 being the question. So I don't know my delta HF, but typically, as I say, you would be given these values. You definitely do not need to memorize these. So atomization of magnesium, typically 148. First ionization energy of magnesium, something in the region of 738. Sometimes you do see variation of these numbers by 1 or 2 digits here and there, depending on which source the values have been obtained from. The second electron affinity, second ionization energy, 1451. That being much larger than the first one, because you're removing an electron from something which has already got a positive charge. Typical AS question there. Why is the second electron affinity larger? Sorry, ionization energy, keep saying that. So why is the second ionization energy larger? Because you're removing from something which already has that positive charge. Kind of like the inverse of the electron affinity answer, where you're created a bond between a negative ion and a negative electron, hence that endothermic second electron affinity. So 1451, we then have the atomization or the bond dissociation energy. So if I'd been given the atomization energy, which is 121, I'd be doubling that to get to 242. You may be given, as I say, either value, just be careful of which you've got. For the electron affinity, I'd have minus 349, and remember I've done that twice, once to each of the chlorine atoms. And then my lattice enthalpy here, I've got a value of plus 2540. Again, if that was a negative answer, the arrow would have just gone downhill and you'd deal with it as such. So if I've got to start essentially where A is there and end up where B is, I've got to follow the arrows in the opposite direction and see which of them I have to change the sign. So the plus 148, its arrow is going from bottom to top, so it's going in the correct direction, as is the second value, the 738, as is the third value, the 1481, likewise the 2 times 121, as also is the electron affinity value. Now that is a negative value, so be careful of that when you put it into your calculator. The one I've got to change is the lattice enthalpy. So to get from top to bottom, which is where I want to end up, I have to invert the arrow, which means that this value of 2540 is going to have its sign changed, which means I'm going to have to subtract that value when I get my final calculation ready. And if I number crunch those values, I will get a final answer of minus 629. Typically these would be kilojoules per mole values, and that would be the final answer. So We can do that for any of these values which are in there. Obviously, we just have to start and stop in the relative position, but we can use a Born-Haber cycle to generate any of the unknowns that we have. The harder part of these calculations is typically looking after the signs, being aware of whether this is a positive value, so this lattice enthalpy value, whether it's positive or negative, and dealing with it as such. And likewise, another one to be aware of is when you have these atomization values for the non-metal, especially when the non-metal is a diatomic molecule, and you may occasionally give the bond dissociation energy or the atomization. And so again, you have to be careful in your manipulation of that value, whether or not you have to double it, or indeed sometimes half it, depending on which value it's asking you to calculate or use. But as we go through this value here, we have a minus 629 kilojoules per mole value, which was exothermic, as we said, but as we said at the beginning, that was a guess. We didn't know if it was exothermic or endothermic. Typically, he says, with a proviso, that typically most delta HFs in exams are of this type, ionic structures are exothermic, but it's in the right ballpark. We've got a value of 600, so 3 digits. If you've got any values which are typically very, very small, so maybe only with a couple of digits, so in the 70s or 80s, quite rare values. Likewise, unless you're calculating lattice enthalpy, you're likely to not have values in the thousands. Typically, a couple of hundred, a few hundred will be rough values for most numbers within a Born-Haber cycle. So you can have a rough idea as to whether you're in the ballpark or not. But we've done 2 examples there. We looked at sodium oxide in the previous example and also magnesium chloride here. And so in the next one, what we'll do is we'll look at more depth at the lattice enthalpy situation, where these values get looked at in more detail and compared with each other, typically comparing experimental values with theoretical values and whether or not our ionic substance is behaving as a true ionic substance. So we'll look at that in the next clip. So thank you very much, and I will see you in that one.